It's my usual. Great. Okay, so today is the fourth and last day of the Virtual Data Academy 2024, and we're going to discuss a bit more on science explorations. There will be discussion of source detection and image display and stuff like this. So rather than giving you nuts and bolts of the Rubin Science platform, we really want to basically walk you through what interesting science bits you can actually be doing. Those are the resources. If more people will sign in, I will just put them in maybe towards the end of my presentation into the chat box. But one thing that I wanted to mention again for the fourth time already is the encouragement for you to provide any feedback about the Rubin Science platform, the usability of it, the activities of community science team, and so on and so forth to the users committee. That's a group that has been charged to solicit feedback from people like you and provide that information to the Rubin operations director, and who I believe is actually on the call today. The charge for the group is listed here, but again, you'll be able to pick those from the slides, from the slide list or link that I will provide you. The users committee is listed on the bottom. One of the users committee members actually presented, Vincenzo Petreka. It was a very, very thorough presentation, so it was really great that we had that person on board. And I think that Matthew Wisner was also on the calls here. Okay, so for today's agenda, there will be two major presentations. One of them is by Douglas Tucker, who's going to be talking about source detection and image display using Firefly. So Firefly is an image display that you might be familiar with if you have paid attention to any of the Portal tutorials. Portal uses actually Firefly for the image display. So this is just another yet connection between the notebook aspect, which is what Douglas Tucker will be doing, and the Portal aspect, which is something you've seen in previous presentations. We're going to take a short break, and then Jeff Carlin is going to provide us a presentation on synthetic source injection into images. That's going to be in Notebook 14. And both of those notebooks are actually available if you log into the Rubin Science Platform notebook aspect, so you don't have to do any special machinations to be able to download them from the delegate repositories as you had to do for the Vincenzo's and for Jake Kurlander's presentations. All right, so before I go any further, I would like to express deep thanks to the organizing committee for this Rubin Data Academy. I think that the presentations are absolutely fabulous. And I'm not patting myself on the shoulder here, but I think that I learned tremendous amounts. So I think that, even though I've been with the Rubin community science team for a good while, so this is very appreciated, and I hope that all of you who are on a call also had a good time and good learning experience. I have a special plea. This is something that you'll hear from me again via email, but we really would like to make sure that whatever the Academy is, you are ultimately the recipients of that. So we would like to hear the feedback from you. So we've created this exit poll, which is listed on the bottom. And basically, it's a Google form. It will not take me more than 5 minutes to fill out. But in particular, what we would like to hear from you is what you would like to see in the future presentations. Needless to say, and the first data coming from this Rubin telescope onto the commissioning camera will be definitely less than a year from now. And at some point, we're going to start getting real data. So I think that to hear from you, what is it that you'd like to get presented on to learn about is very important for our future Rubin Data Academy 2025. All right, so I'm going to once again put into chat the connection to the Google presentation. So in the case if you wanted to go to any of those, here they are. All right, and I think are there any organizing committee members? Do you see that I missed anything for today for this last event, or should we actually just continue and go on with Douglas's presentation? Okay, I don't hear anything from you. So in that case, I'm going to stop sharing, and Douglas, take it away.
Okay, well, thanks, Greg. Let's see. Let me share my screen here. And okay, 1 second. And while I'm at it, I'll open up my chat window so I can see that. Okay. Okay, so we'll start from the usual location we've been starting for our tutorials in the past. I'll stick the link in the chat. So this is the data.lsc.cloud, the interim data facility access point for the Rubin science platform, or the interim data facility, or IDF. I'm starting from the I'll log in here, and I'm at Fermi National Accelerator Laboratory, so that's my identity provider. So I log in through my identity provider, and we will go to the notebooks aspect. So we click on here, and for this notebook, the recommended image for the server is definitely the preferred one, and we don't need a large server, but medium. But let's go with the medium one, and we'll start that up. And this will take a couple seconds. So, so the topic of this tutorial is image characterization and source detection. And this will pop up in a second here. Okay, so I usually like to open up the terminal just in case. And as people know, as people have seen before, this is basically a Unix slash Linux terminal window. But for this particular notebook, we go, okay, once again, I apologize. I have a very messy, very filled home directory, but we want to go to the notebooks directory, and the subdirectory of that is the tutorial notebooks. And in particular, we are going, okay, I'll make this a little bit larger here on this side for a second. We want this notebook, the DP02_05 source detection and measurement notebook. So we double click on that, and it appears over here. And I will reduce this. Actually, since we'll be using two displays sort of side by side later on, I'm just going to close this side window with the list of the directory list in here, and I'll do that by clicking on the folder menu here. Okay, so this notebook provides a brief introduction to running the LSST science pipeline, source detection, deblending, and measurement tasks. Now, it doesn't go into a lot of depth about optimizing these tasks for different types of sources, say point sources or extended sources, but it gives you an introduction. It also covers how to access the footprint of a detected object and how to do force photometry at user-specified coordinates. I won't dwell on a lot of the details. We've seen how to import packages and so on. Of course, we use the NumPy and Matplotlib as many other notebooks we've looked at. And we use the LSST, AFW, and DAF modules to access the Butler and AFW image and AFW display and so on. The things that are new here that you probably haven't seen before are these latter ones that we're importing from the LSST pipe tasks and the algorithms and measurement modules. And we're looking at the characterized image task, the source detection task, the source to blend task, the single frame measurement task, and the force measurement task. So we'll run that. We'll run that cell by hitting Shift Return or Shift Enter. And we'll define some other functions and displays. Previously, we often used for the AFW display the matplotlib as a backend. Here, in this case, we'll use Firefly, and we'll set the AFW's display to be frame 1. So we'll just set this up, and you'll see this new tab is opened up. And it looks awfully like, as Greg mentioned, it looks an awful lot like what we see for the portal aspect. And you can even click on these other things for, well, I guess you can. It doesn't show anything. Okay. Anyway, it's also used for the portal. Now we kind of want to look at the images side by side to the notebook. So what we want to do is we want to, with your mouse, you want to grab this tab. Oops, that was not quite what I want to do, but almost. You want to grab the tab, and you want to move it over here. Oh, that's just not playing well today. Okay, let's try that again. Here we go. Okay, so now we have the notebook on one side of the screen, and the image display on the other side of the screen. And let's move this over a little bit, so because a little bit. And actually, I apologize. I should have made this a little bit larger to be more viewable. So I'll do that now. Okay. Okay, so let's see. Other general setup things. We'll set the plot style to be colorblind friendly, and then we will instantiate the butler. And we want to, as usual, we want to look at in the DP02.2 data repository, and the standard collection that we've been looking at is 2.2i/runs/dp0.2. So I'll run that to instantiate the butler. And now we'll do just a quick look at things. We'll retrieve and display a CaliXP image, or a PVI, a process visit image. And as you may recall, we need to call something from the butler, a CaliXP from a butler. We need to provide a data ID. And for CaliXPs, the minimal thing you need to uniquely identify a CaliXP, a particular CaliXP or PVI, is the visit number, and so the visit's basically an exposure, something like epoch exposure, and the detector. So we're gonna get detector 75 on the simulated LSST camera. So we define the data ID, and then we get to the CaliXP. Now, the CaliXP, as you might remember from previous notebooks, contains the image plus a mask plane and variance planes, and these are useful for detection. And these also report things from the mask plane reports values. It's basically the same size as the image, number of pixels on each side, and each pixel for the mask, as we'll see later, is a bitwise. It's a bitwise mask, and each bit tells you whether there's a detected object. That pixel is part of a detected object, or if it's a bad pixel, if it's a cosmic ray, and so on. And we'll see that a little more of that later. Now, I don't have a whole lot of time, so I'm not going to. I'll leave this to the user of this optional of uncommenting these lines and looking more about what each of these things do. But we have, as I said, we have the masked image, and we have the variance plane, and so on. In addition, we can also grab the PSF mapping for that CaliXP, the World Coordinate System, or WCS, convert pixels to pixel XY to RA and depth, and the photometric calibration, the 0 point for that image. But we won't do that here. And here we will display the image. And hopefully, this has not been working for some reason recently. We'll set this mask transparency to 100%, so that it shouldn't show the mask, but I found last night that it has been showing that. So I think that might be a slight bug in this. Oh, this time it's not showing them. Okay, this is kind of random. At the moment, it's it's not showing the mask. Oh, wait, it does showing some aspects of the mask. There's looks like there's a of a bleed trail mask element being shown. Okay. Anyway, so anyway, here's the image, and you can see if you move your cursor along here, you can see at the bottom of the image, you can see the position in RA and DEC, and also the value in value for the pixel in data numbers. So this is a background subtracted image. And so the values of are generally around 0 data numbers, plus or minus out 100-ish. So Bob Bloom says his does not show the bleed trail. I think it's kind of random. I'm not sure why it does this. It's something to it's something to be. I think we'll need to report. Last night it was actually showing the detection mask throughout, and everything was covered with purple or bluish. But anyway, there seemed to be something a little bit weird there. Okay, but anyway, let's see. Okay, and Greg says that Greg says he does see the bleed trail. Okay, okay. So let's continue on. Now, when we do image processing, we actually want to have we want to put the sky background back in that was abstracted. So we need to so what we need to do is to let's retrieve the background. We can do this using the butler, grabbing the CaliXP background for that data ID. And why don't we display that in frame 2 of a Firefly? And this will pop up here. And now you can see this is the background. And if you actually, I'm gonna make it's a little okay. Let's see. You can click on this thing down in the corner to see. It's another way to see the pixel values. So here in the main image, the sky subtracted image, the values are usually roughly between plus and minus 100 data numbers. Over here, in the background, it's about 3.8 times 10 to the 3 data numbers. So yeah, there's a significant background that had been subtracted. And you also notice there's a trend. There's a systematic trend. It's not a huge trend. And if you look at the data numbers, it goes from about 3.821 data number times 10 to the 3 data numbers to 3.82 about data numbers. So it's not a huge. The lookup makes it look larger than it. I mean, the display makes it look larger than it may really be. Okay, and then now let's add let's add the background back into the original image. Now we just only want to do this once because otherwise you keep on adding the background. And then we'll just we'll display the background, okay, is it actually displaying? Let's try that again. Oh, wait, it's probably hiding. Yeah, here it is. Okay. It's taking a second. And let's see. So another way to see okay, it's the frame is small, so you don't see the data numbers listed here, but we can either open up that other window, or we can increase the size of this until it shows up again. Let's see. Okay, here. Okay, the value now is displayed, and now you'll see the background is about 3.8 times 10 to the 3 data numbers. Okay, so let's adjust the window size, and let's kill off these windows. We can use the little X in the corner. They not immediately obvious until you over mouse them. But then we will empty the Firefly's display. And then for the moment, we will delete this, and we'll grab a fresh version of CalXP later on. Okay, any questions at the moment?
How did you clear the images?
Oh, let me open one up again. Oh,
You just hit the
there's a little, okay, let me,
X.
there's a little X that you click on in the upper right corner.
Got it. Thank you.
Okay. Okay, now we'll do the source detection, deblending, and measurement. The LSC science pipelines tasks the various measurement tasks were imported in the first code, so we don't need to do that again. More information about these tasks can be found at this website, the pipelines.lsst.io website. What we'll do here is we want to create a schema, and so the schema describes the output properties that will be measured for each source that's detected. And the schema needs to be passed to all the tasks, each of which will add columns to when it's done, when it runs. So we'll first create a minimal schema for the source table using this command here. And there's not really much in there. There's a unique ID, RA and DEC, and a unique ID for a parent source for the deblending part. And then we'll also create a container, which will be used for record the metadata about the algorithm execution. So I'll run this. Next, we will configure the different tasks. So each task possesses an associated configuration class, and the properties of these configuration classes can be determined from the classes themselves. We actually won't go into any, I'm actually not going to go into, I'll let the user uncomment these and look at these in more detail, but we'll just move along, and we will set the basic configuration parameters and instantiate each task in turn, starting with the characterize image task. And this characterizes the various image properties like the PSF. So we do that in this cell. We create a config variable for the basic configuration class. In this case, we kind of decide, let's change one of the configuration parameters. So usually you do the PSF is calculated through an iterative process. I think the default is 3, but I don't remember. I'm not quite sure, but we're going to set it to 1 here. And then we will pass this configuration to the characterized image task, and we'll set it to this variable car image task. And then since we don't need the config variable anymore, we can delete that. Likewise, we'll do the same thing similar for the source detection, which detects sources. The default for LSST is is to find things with a signal to noise of 5 or higher. So it's 5 sigma above the detection, above noise background. We'll set ours to slightly a fainter level. So we'll set ours to 4 sigma. Our detection threshold to be 4 sigma above detection threshold, above the threshold, a 4 sigma threshold. So like here, we once again create a configuration class. We set the threshold value to 4, and we set the threshold type to standard deviation. So this would be a 4 sigma detection. And then we pass the schema and the configuration to the source detection task. And then we don't need the configuration variable anymore, so we'll delete that. Next is the blending. The blending converts overlapping sources into parent and child sources. For this tutorial, we don't need to do anything pretty special for here. So we'll just pass the schema to the source to blender task. Then there's a single frame measurement task, which measures the properties of the blended sources. We don't need anything special here, but we do need to pass the schema, a configuration, and remember that that container for containing the metadata for the algorithms, we need to pass that also to the single frame measurement task, and we do that here. Next, we create a source table called, and we'll call it tab. We'll use the minimal schema for that table. We create an AFW table, source table, using that minimal schema, and then we don't need the schema anymore, so we'll delete the schema. Okay, now let's say you've done all this, and you say, oh wait, I want to go back. I want to change the PSF configurations back to 3. Well, you can't just set it to 3. You have to actually go back and reset the configuration. So the configuration parameters cannot be changed after the task has been instructed. But so to change a configuration parameter, you need to redefine it and then redefine the task. So for example, to change the number of PSF iterations done during an image characterization, you need to reset the configuration and then repass it to the configuration task. And we'll kind of skip over these optional things, and we'll jump to grabbing a fresh version of the image of the Kali XP. So we'll do that. We'll grab that again. Now, what we'll do here is okay. This is already run. This Kali XP has already been run through the pipelines. It has its mask bits all set, and one of those mask bits is a detected bit. And so, but we need to clear those all those detected bits out, those bit masks out, so we can read it, so we can run the detection task again. So here we will use the remove and clear mask plane function to remove clear out, reset the detected bits to no detection. Okay, now we get to the meat of this of the source detection. So we will do image characterization first. So we'll run the characterize image task, passing the Kali XP. Remember, it's already been set with the configuration that we set up before, and so it's running. And it finds point sources which are useful for measuring the PSF. And it finishes running, and it returns a result. The result is a structure object, which is basically an struct is just a generalized container for storing multiple output components and accessing them as attributes. So we can look at the type. And yeah, it's a struct. Not so interesting. You can look at the content of the struct using the get dict method. And you see it has exposure, source cap, background, PSF cell, characterized class and background model. It's not so interesting at the moment. And here I'll comment this out. You can look up the contents, and most of it's full of nans and falses. Oh, let's say we want to grab the PSF, recharacterize PSF for a certain point on the image. We can set. We'll look at pixel 1700, 2100 in XY coordinates, and we'll create a point 2D object, which and then we'll open up the updated Kali XP PSF using the get PSF function, and then we will grab the sigma for the PSF using the determinant radius, and then we'll grab the pixel scale in arc seconds, and then since we want full half max, not sigma, we'll use the conversion factor of 2.355, convert from sigma to full width half maximum. We'll print that out. And we find, okay, not the best, but not the worst. It's a 0.97 arc second full width half max at that point in the image. So that's nice. All right, and now let's do the actual source detection. So first we'll run the source detection code, and it's train away. It finds positive and negative peaks. The number of positive peaks is a bit over 2,000 sources, 2292. Now the CST team has played around with this note, trying to do different thresholds, and before we actually tried the threshold 10, and in that case we found if you use a threshold of 10, you get about 940 peaks positive peaks detected. It changes slightly as the algorithms change over time, but it's been around 940. Okay, then we'll create a sources variable to hold the source detection, the sources from the results. And we're gonna take a quick look there, but they'll be mostly nans. So all right, and you actually can also write a fits table here, but we're gonna skip. Well, I'll leave that to the user. Okay, let's run source to blending and measurement and single frame measurement. So first we'll do the source to blending, and we end up with 520 children and end up with 2,500 sources. And then we'll run the source measurement task on all those 2,500 sources. And this will take a few seconds. And it's useful to have the sources all be in contiguous area or sequential area of memory. So we'll copy the sources, and we'll using the and tell it to by passing the true or sign, make sure that copy it and make all the information contiguous or sequential in memory. And then we can do a quick look at this sources in AstroPy table. And we see, oh yeah, RA, DEC, parent, child, the blending, all sorts of interesting stuff. Centroids and so on. Let's see. And now let's take a look at it on Firefly. We'll just look at a bounding, but we'll create a area of a 400 by 400 pixel area centered around a pixel coordinate 1700, 2100 that we looked at for the PSF earlier. So we'll basically create a bounding box. I'll kind of skim over this because due to time, I do want to get to the first detection. We'll create a cutout using a CalXP factory, passing the bounding box. And then we will display the image in display one. Supposedly the transparency of the mask is 100%, but no, I see the detection mask here in blue. But anyway, we'll forge on. And actually, let's zoom in a little bit. Use your scroll bar or mouse pad to zoom in a bit. And now let's plot the sources. And we see the sources circled in orange. Okay, now we'll clean up, but we'll keep the sources and detections for the next sections. I will just skim over the footprints because I do want to get onto the force source detection, but footprints basically are like S extractor segmentation maps. They show you where the detections are, where the area of a given detection for a given source. They can have other information if you have what's called a heavy footprint. Including the various detection of various bitwise masks information. And here's a look at the heavy footprint, but I kind of just skim over that. Here is a description of the bitwise masks I mentioned in the mask plane. So you have a bitwise mask for bad pixel, cosmic ray affected, crosstalk detected, negative, interpolated, et cetera. But I'll just kind of skim over that. This section here's kind of a mask showing things which are detected for this one detected and near the edge for a particular object. But we'll just move over to force photometry, which is also quite interesting. So we have the pipelines have a task for force photometry called the force measurement task. So this task will use the PSF, the image, measure the flux at any user supplied coordinate, a set of any user supplied coordinates. It's not a fit. In since it's not a fit, a flux is returned whether an astronomical source is there or not. And force photometry can be very useful for including sources below the detection threshold or non-detections and analyses. So we'll kind of quickly go over this. We'll create a schema. We'll create a minimal schema again, as we did for the previous detection method. Now, force measurement tasks express a few additional columns currently. Maybe in future versions of the pipeline, it won't require these, but we'll set these. We'll just kind of just take them, accept them, and move forward. We also want to add a flag, which will set 0 for the faint sources, the subdetection thresholds, and we're also going to create a set of random off source coordinates, and we want to flag these. So it'll be 0 for the subthreshold or faint sources, and 1 for random off source coordinate. So we'll click on that. Or do shift enter on that, and we'll create a force source catalog using the schema. Have 0 rows to start, and then we'll configure the force measurement task. There are a few additional plugins beyond the default that are required, and we kind of include these, as is also using a do replace with noise configuration, setting that to false. And then we define. As we did in the previous tasks, we will pass the schema and configuration to the force measurement task, and we don't need the configuration more, so we'll delete it. So this is the setup. Next, we want to define the coordinates. So Scientific motivations for force photometry include measuring a subthreshold or faint sources, or a need for an upper limit on a flux of a time-varying source. The potential drawback of force photometry is that all the flux within the area of the PSF is included, which means that nearby sources can contaminate and add excess flux to the force photometry. And we'll see this a little bit later, further down. For this example, we create a list of subthreshold or faint currents and a set of random off-source currents, which are not near any detected sources. So we'll just look at the areas within 2 arc minutes of the center of the field. So first we'll create NumPy arrays of the right ascension and declination, X, Y pixel currents, and incidental flux and error from our previous list of we created the detected sources earlier on in the previous section. And we'll calculate the signal to noise and for those. And then we'll use a bounding box in WCS to get the central coordinates of the Cali XP, convert the pixels to sky coordinates, and calculate offsets between the sources and the image center. Next, we'll define the maximum offset from the image center to be 2 arc minutes in units of degrees. And we'll find all sources that we detected earlier, the signal to noise between 4 and 5. So these are fainter than the standard detection threshold, but what we detected in the ones that we found in the previous section within the central region. And then it'll define new arrays to hold only the information of the sources to be used for force photometry. It'll clean things up. So here, grabbing just the things in the center of the field with signal to noise between 4 and 5 that we detected earlier. And there's 32 of them. And I add a like number, another 32. So we'll add these to the force source. We'll add these to the force source catalog. Okay, and next we'll create a set of random off-source coordinates for another 32 objects, 32 random coordinates. So I won't go into detail here because I am running out of time, but this cell will create 32 random coordinates in the central region of the image and ensure that they are offset by at least 40 pixels from the nearest detected source. And then we will use the images WCS to convert the random pixels to sky coordinates. And we'll add the off-source coordinates to the force source catalog. And now we have the set of things that we want to run force set of 64 object coordinates, some real, some random. We want to run the force measurement task on. So we do that. So we do that here. So we first we create an empty catalog to store the force measurements, and then we run the task, and it runs quite quickly. Now we explore the results by creating a AstroPy table. We add that type flag that we had before to the table, and let's take a quick look at the table. So we have 64 things, and we have the force photometry run here with all the various columns. Now let's display this the full Cal XP in frame 1. And we'll see what mask appears. Oh, no mask. Okay. This time it actually didn't show the mask. Okay, that's good. And now we'll overplot the coordinates used for the photometry. And we're going to do a loop. We're going to replot this whole thing every time. So we use buffering. So we just plot the points, not replot the image. So we plotted the faint threshold objects as in orange and the random off-source objects in cyan. And you can zoom in a bit on that and see those. Now, why don't we take a look at the force photometry for the compare the force photometry that we just did for those faint objects between things between signal to noise of 4 and 5, which we measured before, and compare them with the force their value, the photometry that we did with the force photometry task here. So we'll do a plot. We'll plot those. So below is the original detection thrust that we flux that we measured in a previous section for those things between signal to noise of 4 and 5. And here is the new measurements. And we see they all pretty much lie along the identity line. There's a few which are above that identity line, that one-to-one line, which will have contamination from nearby objects. Let's see. Why don't we look particularly at those which have differences of at least 20 data numbers above this line. And so we can do that here, and we'll color these. Let's see. We'll color these yellow, and you'll see. Oh yeah. So if you zoom in here, say this guy. Yeah, you see. Yeah, there's something nearby, so that's probably contamination. At least, yeah. So these yellow objects do seem to have contamination. And then finally, let's look at let's look at the flux, the PSF flux for the random objects. These are the cyan objects, those random positions, and those for those faint objects, those signal to noise 4 to 5 objects. And we'll do a histogram, and we can do that here. And not surprisingly, the cyan things, the random things are all kind of scattered. Their PSF fluxes are all scattered around 0. As you'd expect, you calculate the flux of an empty region, it should end up being 0. And the faint sources, they all have positive, definitely positive values for their PSF fluxes. And it looks like I actually made it in time. Okay, so that is the end of this tutorial. Do we have any questions?
I don't see anything in the chat or in the Slack channel, so please raise your hand if there is anything that. What I would recommend that maybe for the breakout sessions, we should have Douglas specifically maybe go over some things that any of you might want to have explained in greater detail. So.
All right. Okay, well, I'll stop sharing screen.
Okay, so if there are no questions, maybe we can take a short break. It is 8:50 right now. So let's reconvene at 9 o'clock Pacific time, and then we can continue with Jeff Carlin telling us about about his stuff, the notebook number 14. So, all right. So I'm going to basically stop and look forward to see you in 10 minutes. All right, at least my clock shows that it's 9 a.m. Pacific time, so we can resume probably at this point. As I mentioned, the second presentation today will be by Jeff Carlin, and he will also go through the notebook aspect of the Rubin Science Platform. So take it away, Jeff.
Okay, thanks, Greg. All right, hopefully you can see my screen share okay.
Looks great.
Okay. So we are going to go through another one of the tutorial notebooks that that you'll find preloaded in your RSP space. So as usual, we go to data.lsst.cloud and we will start up the notebook aspect. You can see I'm already logged in, so it didn't ask me for my login information. We'll select the recommended image, and the medium-sized container should be fine for this purpose. And we'll start that up. So what we're going to look at in this session is injecting artificial sources into the data. And the reason for that, there can be many reasons for that, but one in particular is that because we're looking at a simulated data set for DP 0.2, the particular objects that your research focuses on may not have been included in the simulations. And this is a way that you can just inject those types of sources into the data and then test, the recovery rate or the accuracy of measuring them and other such things. So you'll see examples of a couple of different types of sources that we inject, but it's really not limited to those types of sources. Okay, so we go with the launcher shows up by default. We're going to open the file browser over here, and you can see mine went right to notebooks, tutorial notebooks. And within that, you want to select, scroll, DP02_14, and it's called injecting synthetic sources. So when we double click that, it should pop up, and then we'll just minimize that file browser over there. Okay. So I think I already gave you sort of an overview. We're going to inject into a CalEx image, which is the processed visit image from a single visit. You can also inject sources into COAD images. You can also inject into the raw images before any of the instrument signature has been removed. But we're going to focus on the CalEx in this particular case. Okay, so what we're going to use to do this is a package that is called source injection that is within the Rubin LSST science pipelines. And these tools can be used to inject sources into, as I said, any stage of the imaging. And what underlies it is a software called GalSim, which I'll just go to that link here. It's linked in its documentation is linked in the intro here. But that wasn't very useful. Let's go to the overview. But GalSim is basically a software that was designed to create artificial images of galaxies, stars, whatever, and so that they can be injected into images. I don't know if there are any good examples here, but if you want to read more about GalSim, there are lots of demos and tutorials so that you can learn about what's happening under the hood. We are, going to start off by loading the usual, NumPy, Matplotlib for plotting packages, a few AstroPy packages to read FITS files, to apply units to things, and the tables and sky coordinate. And then you've probably seen many of these LSST packages as well for display, geometry, other such things, and Butler, of course. But then the ones that are unique to this particular notebook are these source injection packages. So there's a tool to ingest a catalog that you've created into the Butler. There's also a tool to generate that catalog if you want to just have it sort of automatically generated for you. And then these are the tasks, these visit inject config and visit inject task are the tasks that the task and config that control injecting sources into the data. Oh, you know, it just occurred to me that I should probably, let's do a little zoom so you can read better. Okay, so then as usual, we're gonna set the plotting to send things to matplotlib and load this color map. And then we're gonna define just one function here that we'll use later on just to rotate an image by some angle. And this is something that you may want to do because the Calyx images can be taken at any arbitrary rotation angle. And so you may want to align things by rotating them. So that's all this function is going to do. We'll come back to that later. Okay, so first thing we want to do is we want to instantiate the Butler pointing to the DP0.2 collection so that we can load an image. The first thing we do is identify an image. In this case, we're just going to pick one tract, and then we're going to do a search for images that overlap that tract that are taken in the G band filter. And from detector 19, remember there are 189 detectors in the LSST camera. So this will pick out things that meet those criteria and give us back a list of dataset references. And we print here the number of them. We found 23 overlapping images. And then I'm just going to randomly pick index 5, pick one of those images. And then we print the data ID to the screen. So you see it's visit 400,440 and detector 19 as we requested. So let's retrieve that image from the Butler using butler.get, and we want the Calyx image, and we give it that data ID that we just defined. And then we want to retrieve some additional information about that image that will be needed to actually inject sources into the image. So you need to know about the WCS, which is the World Coordinate System, the mapping between pixel coordinates and sky coordinates. You need to know the boundaries of the image, this bounding box. And then we need to know the sky coordinates of that bounding box. So that's essentially what all of these are doing. So you can see you use the WCS to convert the corners of the bounding box, which are in XY, to sky coordinates using this pixel to sky. And then here we actually create an AstroPy sky coord object of the central coordinate of our Calyx image. And then we want to know how large it is on the sky because we're going to generate a catalog of artificial sources. And so we want to know how large an area they should span. So you can use this bounding box method called getDimensions. And then you multiply it by the pixel scale, which comes from the WCS, and convert that to degrees. And that tells you that the image is about 0.2 degrees on a side. So we'll use that information in just a minute. We've saved it as a variable called msize. Okay, so now we have the image. We know we've characterized it a little bit. Now we want to set up a source catalog to of a list of sources to inject into the image. And so here we're going to use a tool that comes from the source injection package called Generate Injection Catalog. You could also just create this table yourself. This is just a convenience function, this Generate Injection Catalog, that makes it easy to create, you know, a very large catalog if you wanted to. And so we're going to set the radius to be half of that roughly 0.2 degree image size that we saw earlier. And then we get to the fun part here. We're going to do 3 different things. We're going to first inject simulated galaxies into the image. Then we're going to inject some simulated stars. And then we're going to actually take an image, an observed image. We're going to take an observed image and actually inject a postage stamp of that image into the data. Thanks for the question, Lily. And there's really no reason. I think it was to do 0.2 over 2 instead of just 0.1. I think it was initially, or I think it's just kind of for clarity, just to remind you that it's a radius and not a diameter, but totally no particular reason otherwise. Okay, so for galaxies in GalSim, you can do very complicated things, but the simplest form of a galaxy in GalSim is parameterized by a Sersic model, which has a profile like this. So this is the intensity of light here as a function of radius. And so you have some central peak, and then you see that things fall off with radius as 1 over n, essentially, e to the 1 over n, I should say, or e to the r to the 1 over n. But so if the n is 1, this just becomes an exponential of r. If it's n is 4, you may recognize that as a de Vaucouleurs profile, a classic sort of galaxy profile. So this just, the n characterizes how fast the light falls off from the center as a function of radius. And you can see there's a half-light radius, which is, as it says, the radius at which half of the light is contained. So you can also specify an axis ratio. So this is just parameterized in terms of radius, but we're going to also specify an axis ratio of minor to major axis so that you can get elongated galaxies. And that ratio is parameterized as Q, and then you can specify the rotation angle of the galaxy on the sky. And so when you use this generate injection catalog, I'll just go here and just highlight it in the cell below first. I can feed it a list of magnitude. Okay, I want magnitude 15. This is the Sersic index n. So I want 3 different values of that, 3 different values of the axis ratio, 2 values of the rotation angle, and 1 value of the half-light radius. And then basically, oh, and number equals 2. So basically then what this task is going to do is it's going to do all of the combinations of these parameters. So it's going to take 2 times 1 magnitude times 3 different Sersic indices times 3 different times 2 times 1. And so that you end up with 36 different combinations of those parameters. Sorry, this is 36, and then the n equals 2 does that twice. So you end up with 72 objects. And so this is just a convenience where if you wanted to generate 10,000 galaxies to inject into an image, you can do that very easily this way. Okay, so then the other thing that you need to provide to this generate injection catalog is the minimum and max RA and DEC coordinates. That's why we defined that inject size and the central coordinate in RA and DEC. So this is just center minus inject size, center plus inject size in both coordinates. And see here that we've said source type equals CERSIC. So we're specifically saying we want that galaxy model. Here we explicitly set the random number seed so that you and I can both run this and get the same result. But if you don't set that random seed, then it is actually going to be random. And it's going to select random positions within these boundaries in RA and DEC. So I'm going to execute that. And it said, oh, I was wrong. It was, yeah, so there's 18 of these generated 2 times. So it is 36. Okay, so we have, this says it generated a catalog containing 36 sources. And then we're going to do the same thing for stars. And in this case, we're going to specify 5 different magnitudes. And then we say source type equals star. And we're going to say do that 7 times. So this will do 5 magnitudes times 7 should give us 35 stars. And we set, again, we explicitly set the seed just for reproducibility here. But okay, this gave us 35 stars. And now we've generated 2 catalogs.
Hey,
And,
Jeff,
oh, yes.
will it make a saturated stellar profile if it's too bright, or it just puts the full star in?
That's a really good question, actually. I'm not sure, because I would think that the 16th magnitude might possibly be saturated. My guess is it doesn't know how to do saturation properly. So it'll probably actually give you a properly shaped star that shouldn't be properly shaped.
Yeah. Thanks.
Sure. Yeah, so then we're going to go on, we're going to take a look at that catalog. We'll use the AstroPy, the VStack, which is, because these are both AstroPy tables that were created, we'll just stack them together using that method and then take a look at it. Okay, and so here's that catalog that we generated, the combination of the 2 catalogs. It just assigns an ID to each one, the RA and DEC, and you see the source type that we specified, and we have CERSIC and star, and the magnitude we specified. And then you can see that for the star, hopefully you can see, there we are, for the stars, the parameters that aren't needed, like the CERSIC index and rotation angle and stuff like that, are just blank here. So really for the star, all you need to know is the magnitude, and it's going to convolve in this case, a delta function for the star with the PSF and inject something that will look like a stellar image. And you'll see that in a minute.
Hey, Jeff,
Oh, yeah.
when these tables print out and they're truncated because they're too long, how do you force it to give you the full table or a particular part? You just have to print a certain range?
That's usually what I end up doing. Other people might know of a better way of doing that. But yeah, I might usually just like print,
there is a way to set it. I'll let me hunt that down.
I know you can do that for pandas data frames, but I don't know if it works, or if there is a way to do that for AstroPy tables. Maybe there is.
Thank you.
Yeah, that's a good question, because it is often annoying having this little truncation and not knowing what's happening in between there. Okay, when we're going to inject one more type of source into the data. In this case, it's an image, an actual image, telescope image of a galaxy. But really, you can inject any image into the data as long as it's an image that's in FITS format and has a defined WCS. Remember, that's the mapping from sky coordinates to pixel coordinates. So I'll show you an example from our documentation. This is an example of the Rubin Observatory logo injected into an astronomical image. In our case, we're going to inject this image from, let's see, if I go to NED, the NASA Extragalactic Database. Where did we go? Images here. We're going to inject an image that I downloaded from here, and it's going to be this SDSS G-band image. So it looks like this. It's a nice little galaxy image. So we've downloaded that, and it's provided in the data folder that comes along with your tutorial notebooks. So just to give you a look at it, we use the FITS utility from AstroPi and just read that image in, and then we'll just display it with mshow here. And there you can see it's a nice spiral galaxy. So to inject that image directly into the DP 0.2 image, we just create one more entry in our table. We're going to just give it an ID of 9999. We're going to randomly pick an RA and DEC position. And then the source type is stamp, because it's a postage stamp. And you can tell it the brightness to scale it to. So here we said magnitude 14.8. And then you just tell it the path to that FITS file that contains the image. So here we just give it the path, which is data/pgc blah 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 .fits. And again, this is we're creating this as an AstroPi table based on this dictionary of information. So we create that, and then we do the VStack thing again to just add that entry to the bottom of our list. And now you can see it should say there are 72 objects in the list. And now you can see at the bottom, we have the stamp. And you can see its path to the actual file. One more thing before we get to the that's a very good question. I was wondering the same question in my head, Sean. I'm not exactly sure how, for the stamp images, how the magnitude is interpreted. Or in fact, even whether it is interpreted. So, I mean, I guess it has to be somehow, but it must just be the total flux of the stamp is scaled to this magnitude. So that would include the background stars and other, and the main galaxy. So my guess is it has to do the entire, the total flux in the stamp to scale it. But I'm not positive about that. We might have to look at the GalSim documentation to find an answer for that. Okay, one other thing we're going to do is just to show you how, if you wanted to take that postage stamp and rotate it to a different angle before you inject it, that's what this brief section does. I'm going to just do it really quickly because it's just kind of a convenience. But basically, we're just going to use that rotate exposure function that we defined above, where you read the image. So this is the original image. We can ignore this warning. It doesn't matter. And then we just apply some random rotation angle. So I'll just give it 57 degrees. And that function that was defined above just takes the original image and the rotation angle, and it'll return the rotated image. And essentially what that's doing is it's doing what's called warping the image to a different WCS. It essentially has to resample all of the pixels in the new rotated coordinate system. And so we can display the original one and the rotated one next to each other and see that succeeded. It rotated by 57 degrees. So if you wanted to rotate the postage stamp before injecting it, this is a way that you could do that. And so you could then save this and then inject a rotated version. So we'll do that. We will first replace all of, because when it does this, it pads the region to the entire necessary region. We'll set all of these regions outside the bounding box of the original image. They're set to nans, to not a number. We'll set them to zeros instead. So that's all this this line is doing, is setting those to zeros, because otherwise it'll fail in the source injection. And then we're just going to use the write fits method to just write that out to our home directory. And then we're going to add one more entry to the injection catalog for that image. So now we're going to inject 2 postage stamp images and do the thing to stack the catalogs again. Okay, so now we get to the part where we actually are going to do the source injection. The first thing you need to do is you need to register, ingest this source catalog that we created into a Butler repository so that the pipeline tools know how to deal with it. So the first thing we're going to do is we're going to generate a collection, what's known as a collection in the Butler for this particular process that we're going through right now. There's a note here that that if you provide a collection name that already exists in the Butler, then the task will complain that this already exists, I don't know what to do now, and it won't write a new thing. So you need to provide something unique. So in this case, let's put today's date, which is 06/21. If I put that at the end of the name, I guess provided I only do it once, let's do 06/21A. That should be a unique collection for now. So this is just creating this is just a string that has u slash and then your username, which we got from this operating system call here, and then test injection inputs. So then we go to the Butler. We make a writable Butler, meaning we instantiate a Butler, but we say writable equals true because we need to be able to put the outputs of the task into this Butler that we're going to initialize. And then we are going to ingest that catalog that we created. And so that uses this ingest injection catalog. That's a tongue twister. So for that ingest task, we tell it, this is the Butler that I want you to ingest into. We feed it the table that we created. We tell it what band we want it to calculate magnitudes in and what band of images to find to inject things into. And then we give it the name of the output collection, which we defined just above here. And then the reason for this conflicting definition error, this is what will give you an error if you if the collection already exists in the Butler. In our case, we gave it a unique name, so it'll say, here we are, we ingested one injection catalog. If I execute this again, now it's going to say, oh, I already found a collection with that name. And so, and it tells you it didn't ingest a new catalog, but since we already had a pre-existing catalog that we just ingested a minute ago, it's fine. It's already there and ingested. So we'll continue with the one that we ingested the first time. Okay, so now the Butler has the catalog of sources to inject. Now we're going to run the source injection task. It needs some additional information about the image, as I mentioned earlier. It needs to know about the point spread function, the PSF, because it's going to convolve everything with the PSF so that you get something that looks appropriate for the on-sky imaging that you're injecting into. It needs to know about the photometric calibration so it can convert magnitudes to fluxes, so that you retrieve that also from the CalX that we retrieved earlier. and it needs to know the mapping from pixel to sky coordinates and vice versa. So we load the WCS from the CalExp. And then just for convenience, let's just load those injection catalogs that we ingested into the Butler. So this just shows you how to actually go and query the Butler for that collection. Oops, sorry, for that collection that we created. And then the results of this query, we just wrap it in a butler.get and grab all of those injection refs. So this is just convenient to have the catalogs in this injection catalogs list. Okay. As I mentioned, you can inject sources using this task into coad images, and then you use a different task than what we're going to use here. You can do it for coad images, for the exposure, the raw exposures, for visits. We're going to do visits, a CalExp image. We're going to do visit inject. And so as you've seen in Douglas's tutorial right before me, when you run these pipelines tasks, you first instantiate the configuration and change any configurations if you want to. And then you instantiate the task itself, and then you'll execute it. You'll run it. Yeah, Bob.
I've lost track and am somewhat confused. I think we have the original DC2 image for DP 0.2. We have the stamp from Sloan.
Mm-hmm.
We have the original list of injected sources. So how does it manage convolving those all to the same PSF?
It essentially just will loop over that list of sources. Well, I'll show you. It's easier if I just show you the part here. So first we instantiate those, the configuration and the task. So now we're going to run inject task here in a second. And so you can see here, you give it, when you call that inject task.run, you give it the list of sources. So you give it that injection catalog. You give it the exposure that you want to inject into. And in this case, we clone it so we're not overwriting the original one. And then you give it the point spread function and the photometric calibration and the WCS corresponding to that image. And so you pass those to the function so that it knows which PSF to convolve with, which photometric calibration to apply, and all of that. I think, did that address your question, Bob?
Except how does it handle the Sloan image?
It should just be convolving that image with the PSF and scaling the flux as well. I'm not exactly sure what GaussM does under the hood there, but it should be essentially just taking that image, because we gave it the path so it knows where to go and read that image. And I think, yeah, it just convolves it and scales the flux.
Sloan image is almost certainly worth seeing, right? So at the level.
Yeah, so I suppose the convolution is not doing anything at that point. And you can actually see the edges of the postage stamp. You'll see in a minute. Okay. So I think, like Sean was asking earlier, how that magnitude for the postage stamp is interpreted. I think it's scaling the whole image, like the flux of the total image. So that's why you'll see the edges of the stamp. So it's not the most ideal case to use a postage stamp from another telescope, but you could use simulated image, for example. Okay, so we're going to run the task, and I think I just went through what we passed to it, and then we just send that to something called injected output. And then after that returns, we're just going to extract the output exposure, so the actual image and the catalog from that. And so when we run this, it'll take it a little bit. And so it says it retrieved all of the sources. Turns out one of our random coordinates was outside the image's bounding box. So it's going to skip one. And it's going to add new mask planes to the image to show you where injected pixels are. This is seeming slower than I'm used to, but we'll let it run. And then after it's finished, as I mentioned here, we passed it a clone of the original image. So after this finishes, we'll compare the original image and the output exposure. I guess we have time for questions while it executes. And you can see here that it, under the hood, knows how to interpret. When I said I want star, it knows how to pass delta function to the Gaussian. Okay, so in injected sources, some sources, because we did random coordinates and apparently we're not careful enough, a few of them, it's smart enough to say, oh, this one doesn't overlap the image, or a couple of them reached some size limit. I think I did create some really big galaxies, and so they reached some size limit that caused this flag. So it injected 64 of them. We could explore those flags a little more afterward. So as I said, we're going to just display the two images next to each other. That's all this is doing here. And okay, this was the original image on the left. It's the full 4K by 4K pixel image. And this is the one with sources injected. And you can see there are long extended things. Those are the I guess it'd be very low axis ratio objects at different rotations. You can maybe tell that they're stars. And you can maybe tell that these are the two postage stamp images over here in the lower or middle right. If you instead comment out this line, it'll zoom on those postage stamps so you can see what that looks like in more detail. And so you can see that it, I think it just scales the flux up of the entire image. And so you can see the stars that were in that image and the galaxy get scaled up, and you can kind of see the boundaries even. But but anyway, that shows you can see the image that the images have been injected. And then the last thing I wanted to do is just to see what the injected images look like without the original image. Well, let's just go ahead and apply the difference imaging tasks from the pipeline and subtract off then a template image and see if the sources that we injected remain after doing that.
Jeff, there's a question from Sarah Johnson in the chat, and I think that might be related to the question that Bob Bloom was asking earlier.
Ah, I see. Where can I find information regarding the format of the PSFs included in the FITS images? That is a very good question. Let's see, these would be PSFX. I don't think in our documentation there is anything. So I think, I don't know, we'll see if this works. PSFX user manual. So I think you would need to go to the PSFX documentation itself. So because I think we don't necessarily reproduce the documentation from that software. But I'm not sure what exists in our documentation. So we could take a look at that after. We can, let's see, we have one of them loaded. And so once remember we grabbed one, we said PSF, I'll do it again. Calyx G dot get PSF. Yeah, so when I just do that, it says, okay, yes, this is a PSFX PSF. You can see the if you just do, dot and then hit tab, it shows you all the methods that are associated with that. So at least this shows you how you can learn more about the specific PSF from this image. You can compute an image of it, a bounding box, etc. And we do have a tutorial notebook. I think it's 13 A and B that show you how to work with the PSFs. And so, yeah, you can see you get a little more information from the methods that are associated with it. But otherwise, if you need really nitty-gritty like details, I think the documentation from PSFX is what you would need. Okay, so the last thing we're going to do is we're going to do difference imaging. And so template images are created, they're co-ed images of a particular region of the sky, but they're created from the typically from the images that had the best seeing. So they're the highest quality images we can make. And so those are called good seeing diff template exposure. And so you can load those. Remember, we have the data ID for the Calyx image that we're using. I'll show you that again. Remember, this is the Calyx image we've been using throughout. It's from the MSIM instrument, detector 19, visit blod, band G, etc. And so you can give that same data ID to the butler.get call, where instead you ask it for the good seeing diff template exposure. So now we have the template exposure and we have the injected image. Now we're going to use this image subtraction task called Allard-Lupton subtract. And so as you've seen, we first initialize the configuration for that task, and then we feed that configuration to the task itself to initialize the task. And here I just pointed science exposure to the injected exposure that we retrieved before. And you need to give it also a list of the sources in the image. And so here we use that same data ID, that data ID G, to load the source catalog from the original Calyx that we are looking at. And then the result of that Allard-Lupton subtract task, after we run it, should be a difference image created by subtracting the template exposure from the science exposure, scaling it appropriately for the relative PSFs and background levels, etc. And so we'll execute that, and it does take a second because you can see it's, renormalizing things of, 16 million pixels and doing a bunch of convolution and things. And it will give you an update here as it runs. And hopefully not take too long. Okay, so if I move on, when this completes, we'll have it just plot the resulting image. So we'll actually just plot the original Calyx image the injected image and the difference image next to each other, all three of them. So we'll do that here, and we're setting some values, some X and Y values, just to zoom in on a 1500 by 1500 pixel range. This is totally arbitrary, but just to make it easier to see the differences. So that's what we're going to execute this here. It's just creating 3 panels of subplots and showing the okay, this doesn't seem right. This should say CalX image, or it's displaying the wrong thing. The CalX with the synthetic sources and then the difference image. So yeah, this is not the template image. This is the original CalX image. So there's the CalX. There's the one with the synthetic sources, and if you subtract this from this, you get the new image, which you can see all of the floofy galaxies and the long toothpick galaxies that we injected, but you can also see the stars that we injected now. Those remain in the difference image. And that was where I wanted to stop. So yes, Eric, why is the source catalog needed for the image subtraction? Is it for PSF matching of the images? I think that's exactly it. It's so that you can go and actually create the convolution kernel based on the relative PSFs. So yeah, you can see here it's saying blah, blah, blah sources selected for PSF matching. Okay, and so that was where I was going to stop. You can imagine for your analyses, you might want to go on and do essentially what Douglas demonstrated earlier today, and actually execute the source detection and measurement pipelines on the sources that you've injected to see how well you recover them, how well you measure their properties. Of course, you could, as I mentioned, you can inject into coad images or into the raw images or other things. And of course, you can inject other types of objects. You can get more complicated than my random selection of weird galaxies. You can apply, for example, shear to the galaxies. There is a model for that in GalSim, so that you can actually then try and do your weak lensing studies and other things. So I will stop there and see if there are any additional questions. Thanks for your attention. Oh, let's see. Yes, I see a question from Sean. In the difference image near 1300, 2300. Ah, yes. Is that an original source that wasn't subtracted properly? Yes, it is indeed. It's a bright, probably saturated star that doesn't subtract properly in the difference image. Probably, if we looked at this image, you would see the bleed trail. Yeah, and that is a good point that, things don't always subtract perfectly, especially saturated things. They're complicated. But otherwise, it actually looks really good. Yeah, any other questions?
I don't see anything on Slack channel or in the chat, but I think that maybe this is a good time to take a break and return. So today we're going to, again, set up a few breakout rooms. If there's anything that anybody would like to discuss sort of in teams or in groups, we certainly can do that. But I would recommend that we have 2 breakout rooms where we can actually sort of go through maybe some more detailed and more expert questions, both for Doug and for Jeff separately. So that's what I will do. And if there's anything technical, I will also stay in the main room for the time being. So we'll see you in 10 minutes at 10 o'clock or 11 minutes, whatever. And I will set up the breakout rooms in the meantime. Okay, everybody. Thank you. All right, I suspect you guys are coming back from the break from your visit to the coffee machine and all that. At this point, I opened up a number of breakout rooms. I think there's one for discussion with Jeff with more regarding more details of the source injection, one for Douglas to talk more about the source detection, and also maybe some details of the Firefly image display. I will be in a main session, a main room, because there might be some questions from previous days. And if you would like to do any kind of co-working with any of your colleagues, we have a couple spare rooms and then one more in a case if need arises at some point, so I can rename this in the future. So go ahead, join in, and I will be here in the case if there are any questions that came up on any technical issues.
Oh, Greg,
Yes.
will we be rejoining the main room later on?
Yes, please do rejoin the main room later on. I will be hanging out in the main room all the way through 11 o'clock Pacific time, but in a case if you need to sign off or anything like this, that's fine. That's not an issue. So I don't have anything specific, no specific agenda. Let me just stop recording because I think that's probably not necessary at this point. So